for another installment of our Cold Blast episodes. Just a disclaimer, you are going to want to grab a pen and a piece of paper for this one because we're doing some math.
To school.
We're going back to school. We're doing some math. Today, we are going to figure out how to know your airflow. Tell us, Lou.
All right, know your airflow. So, common thing is, technicians are out there going to homes, existing systems, existing ductwork, and so they're not the one that designed the system.
Mm-hmm.
So, but customers complaining about possible problems, or not enough cooling, not enough heating, not enough comfort. One of the most important things you can know, and it's a lot of times everybody wants to blame the equipment, but the equipment's only good as its ductwork. Mm-hmm. And the duct system is very important, and to know what that duct system is doing for you is very important as well. So how do I know my airflow if on an existing system without actually running all the sizes, all the runs? It's a lot of work. So there's an easy way to figure out what the airflow is in a system. And whether it's an air handler or a gas furnace, we can do it with either, as long as the air handler has electric heat installed in it, which most of them do. It'll be like usually a heat pump system. Mm-hmm. So one thing, rule of thumb, is just when you're looking around a house, usually most basements in our area have an exposed duct system in the basement.
Right.
If you have a 3-ton unit, you want to at least see 12 6-inch runs off of that, because formula we all learned in school was 400 CFM per ton. Kind of now, with the efficiency being a big thing and dehumidification, the other number you could work off is 350 CFM mm-hmm. per ton. But it's always been traditional for every ton of air conditioning, you need 400 CFMs. So, and traditionally, a 6-inch duct run, like round pipe, which is very commonly used in most homes in our area, provides about 100 CFM.
Okay.
So you want to at least see 12 of those in a house, or bigger sizes like a 7 or 8-inch equivalent if it's rectangular duct. So first off, just to get an idea of what your airflow is going to be just to look those things over and get a count on those.
And from a mental perspective and an analysis, that's just kind of getting yourself in the mental ballpark of where you think this airflow is going to come out
where it's going to be. Right. And a lot of the other part of it is just listening to a blower in a system. A lot of seasoned techs can tell, is that thing working hard, how noisy it is, how quiet it is. But let's say we want to know what the CFM is going through this system right now, and we don't want to, and we want to use the resources we have. So the resource we have are, let's start with a furnace. So if a furnace, we already know the BTUs of that furnace mm-hmm. because it's going to be on the data plate. So knowing that, we're going to be able to use that as a source to find out what our airflow is. So basically the formula, so you run your pen, you get your pencil and paper out for this.
Start scribbling.
So the formula is, first you want to look at the data plate of the furnace. Our example now is going to be 60,000 BTUs.
Okay.
So 60,000 BTU furnace, and let's just say it's 96% efficient. So first formula we're going to do is take that 60,000 BTUs times 0.96, because we want to know what the output of that furnace is.
Gotcha.
So the output of that furnace would be 57,600 BTUs. And I do this in my classes, and guys, this is a real popular section, so hopefully everybody's going to get something out of this. So let's just write that number down, 57,600, and let's just put that aside for the moment. So the next thing we want to do is, even if it's summertime, you're just going to explain to your customer, I just have to run a test. I'm going to put the furnace on. So we're going to run the furnace for maybe 10 minutes. And what we're going to do is we're going to run the furnace, let it heat up, and then we're going to take a temperature rise. So the temperature rise is the differential between the return air temperature coming into the furnace and the supply air temperature leaving the furnace.
So it doesn't matter, Lou, what that set temp, as long as the mode is heat.
As long as the mode is heat and the furnace is on, you want to
because you're just testing the delta, so it doesn't really matter what the temperatures are.
Exactly.
Gotcha.
So we're testing the delta, as Brendan said, and that I usually like to take the supply temperature right out of sight of the heat exchanger itself, because you can get different numbers that way.
Sure.
So let's say our delta on this particular system ends up being 58 degrees. So now we're going to run another little math formula. We're going to take that 58 degrees, and this is just a fixed number. It's just part of the formula. The fixed number is 1.08. So you're always going to use this number 1.08 times the delta.
Okay.
So the delta is 58 in this occasion, and we're taking it times 1.08. So that's going to end up coming out to 62.64. So now we have that number. So we're going to take that number and we're going to divide it. We're going to divide 57,600 divided by 62.64. Now that total number is going to be the CFM that system's running at.
Gotcha.
And in this case, it's going to be 919 CFM. So that's going to give you, so you have an idea of what your system's doing. Now the other formula would be if you have an air handler. So Lou, I don't have, it's on a gas furnace. It's an air handler. So I got kilowatts and not BTUs, and I'm looking at. So let's just say same formula, same idea, but now we want to take what our electric heaters are. So our electric heaters, let's just say we have a 15 kW heater set up. And what we want to do is we want to take, now 15 kW, since there's a variable of your incoming voltage, your L1, L2, it doesn't mean it's going to always output the same. The lower the voltage, the lower the output. The higher the voltage, the higher the output. So what we want to do is take the actual voltage that's coming into that heater section in that air handler.
Okay.
So let's just use a basic example, 240 volts. You'll very rarely ever see 240 volts right on the money, as most techs know, but we're going to use that for the example. So let's say we have 240 volts, and our amp draw is 60 amps. So that's going to come out to 14,400 watts. So basically, that's where you get your 15 kW.
Okay.
And then we're going to times that. So we want to turn that into BTUs because our formula requires us to use BTUs, not watts. So how we turn watts, and anybody can do this at home. That's not even a tech. So you want to know what your little electric heater's putting on. Just take the watts, how many BTUs you're getting out of it. Take the watts off of any electrical piece of equipment, and times it times 3.413. That's a fixed number. And when you take the watts times that number, 3.413, it's going to give you the BTUs.
Cool.
The BTUs in this case is 49,147 BTUs. So now we have our BTUs. So we got the BTU number, and we're going to take the temperature rise like we did, the delta T.
Same deal.
Same deal. Take the time 1.08, and then we're going to get a number. In this case, we had a 40 degree, for our example, 40 degree temperature rise times the 1.08 became the 43.2. And we divide 49,147 by the 43.2. And in this case, we got 1,138 CFM. So it's an awesome little formula. It takes, you have it on a little piece of notepad, and very, very effective on finding out what your actual airflow through your duct system is, and having a fixed operation sequence to be able to find that. And the other part of that would be static pressure as well, which we can do that another time.
Teaser.
All right, another teaser.
Thanks, Lou.
All right.